Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole.
And I'm Brian, and we're both from Calgary, Alberta, Canada.
Thank you again to our Patreon subscribers. We really appreciate your support.
If you're not a subscriber, for less than the cost of a reusable face mask, which most of us have a collection of now, you can hear us talk about more interesting engineering failures.
You know, last fall 2020, I was buying face masks and I thought to myself, I don't need to get any Christmas themed ones because I probably won't be wearing masks next Christmas. And then here we are.
How many Christmas themed ones do you have?
Only a couple, because I didn't want too many, because again, I thought I wouldn't wear them. They're more winter themed. There's a few with snowflakes on them and one that kind of looks like wrapping paper. I just wear them year round because I think they're fun. But yeah, here we are.
I have some very fashionable ones that have flowers on them. One of my colleagues, she actually made these face masks with flowers on them out of, I believe, old couch fabric.
Oh, cool. Although weird. Do they smell funny? Couches smell funny.
No, it was just like fabric you would put on a couch. Like if you were making a couch from the 70s that have flowers on it. Yeah, she didn't take it off her couch. It was was that style of print. But I've got a few comments on them, so they're very fashionable.
I thought she took the fabric off her couch and made them. And I was like, oh, that's weird. Someone's butts could have been sitting on them.
No. I think this was just like excess fabric from making couch pillows or doing something.
Anyways, yeah, less than a cost of a reusable face mask, also known as $5 a month. You can hear us talk about more interesting failures. They're really fun episodes. Lots of train tangents, lots of plane tangents. You know how we love those. So please come on over and check it out. Support our show.
That's $5 Canadian.
Yes, Canadian. So if you're in America land, that's like extra cheap. Like maybe even $3. I don't know what the exchange is right now. This week in engineering news, a self-powered stretchable thermometer.
Ooh, that sounds really cool.
It is pretty cool. So as we develop soft robotics, smart clothing, and other biocompatible medical devices, we need flexible sensors that can move with us and move with the different fabrics that we're using in these devices. But most of today's sensors are rigid and they're not very flexible. They don't move. They kind of hurt when you lean on them. So researchers at Harvard John A. Paulson School of Engineering and Applied Sciences developed a soft, stretchable, self-powered thermometer. The device has 3 parts. It has an electrolyte, an electrode, and a dielectric material in between the two. And the ions accumulate between the electrolyte and the dielectric material, and then electrons accumulate between the electrode and the dielectric material. So the imbalance of this charge changes the thickness of the ionic cloud, generates a voltage, which translates to a change in temperature. The thermometer can measure temperatures from 200 to minus 100 degrees Celsius, which is a pretty big range. And that means that these devices can be used for a million different applications, which is so cool. Think about in the not so distant future, you're wearing a watch that's completely flexible, you know, and it's like wearing a soft bracelet, but it tells time and it takes biometric data, takes your heart rate, you know, can measure your body temperature, you know, steps walked per day, et cetera, but it's no longer this solid rectangle or square that you're wearing on your wrist. And now it's soft and flexible and it can move with you. So that's something that's one of the potential applications that I keep kind of coming back to in my mind.
I think that sounds really neat. Or for, tracking, athlete data for various sporting events, or if you were going on a run or a hike or something like that. Yeah, just having all that data in this flexible format, because it sounds like it will be fairly flexible.
Yeah, I have an old Garmin watch before it could measure your heart rate on your wrist, and I had to wear a band that you would wear and it would measure your heart rate, but it was this kind of, it was a little bit flexible, but it was very uncomfortable to wear, and I really didn't like wearing it, so I was really happy when I upgraded.
Yeah, I had one of those as well, and now the watch that I have, it does support the band, but it also just does the heart rate measurement just right, I guess, underneath the watch, kind of on the wrist. So having all of this data is really cool. And yeah, like Nicole said, even 10 years ago, that didn't really exist. If you had heart rate data, it was via the band that you wore around your chest, and then it either had to be connected to your watch physically, and it wasn't automatically connected through Bluetooth.
Yeah, as much as the band was uncomfortable, I think one of the more annoying parts was that you had to put it on and then get it to connect to the watch before you could do any activity. Whereas now I can just put my running shoes on and go out for a run and my watch is always ready to go, which, I mean, of course, first world problems, but I do think that's really handy. And it's nice to have all the data as well. You know, I'm not an Olympic athlete or anything, but it's nice to know how many steps I go in a day, how active I'm being, when my heart rate is spiking, what types of activities I'm doing to make it spike, what my stress levels are, etc., etc. So I think there's a lot of really cool applications for this product, and I'm excited to see what they do with it. So if you want to read more on the soft thermometer, check out the link on the webpage for this episode at failureology.ca.
This episode of Failureology is brought to you by Shorts.
They're shorts that are short.
Made by Shorts.
Not to be confused with pants. These are different.
This seems pretty self-explanatory from the name, but yet, here we are, trying to fill the next 15 seconds of advertising time.
Now on to this week's engineering failure, the Harbor Cay condominium collapse in Cocoa Beach, Florida.
I've got to say, when we started researching this episode, we had a pretty good idea what we'd find. 9 times out of 10, a building collapse is structural. But going in, wasn't really sure if there'd be enough information for a full episode. Sometimes these types of failures have kind of straightforward causes. And also this happened, back in the early 80s. And so I wasn't sure if there'd be information available. But luckily for us and luckily for you, there's a ton of information. There's a lot of things that went wrong. It almost seems like anything that could have gone wrong with the structure went wrong. And so here we are with a regular episode. So buckle up, folks. This one's a good one.
So Cocoa Beach, for people that aren't familiar with Florida like me, it's located south of Kennedy Space Center and east of Orlando. So the Harbor Cay condominium was a 5-story plate condo building that collapsed around 3 p.m. on March 27, 1981, killing 11 workers and injuring 27 people. So the collapse occurred as they were constructing and pouring concrete for the roof slab. So they were almost done building this building, and the building fell down.
That's how bad this structure was. They didn't even finish the structure, and it fell down. That is really bad.
Yeah, and so the collapse, the origin point for this collapse, it appears to have originated in the area where they were pouring concrete for the roof slab. Several of the survivors in the building, they described building trembling a couple times that day with a large pop, then a rumble as the roof caves in, and the collapse traveled as a wave until it enveloped the entire structure. So I'm imagining this, they didn't really have there was no video we could find from back in the 1980s, but I'm imagining it like the building implosions that, controlled building implosions where each floor kind of collapses down on the floor below it. In an implosion, it's in a controlled manner, but this one was not supposed to collapse.
Yeah, the technical term for that is pancaking, where one floor basically lands flat onto the next floor and pancakes itself down until you've got a stack of pancakes at the bottom. Not good.
I think it's really neat watching the implosion videos, especially in built-up areas where they're taking this structure that's 10 or 15 or 20 stories tall, and obviously it can't just tip over, so it has to collapse on the building footprint, and they manage to do this in these built-up areas. I always think it's really impressive the engineering work that goes into figuring out where to place the charges and what pillars to cut.
Yes, except no one's in those.
Yes, or on top of them, because in some of the notes from this building collapse, some workers rode down on a dry form near the south end, and as this worker was riding down, which you shouldn't be riding down on a roof slab, he could see the middle of each floor giving way as each floor collapsed. So as he descends on the roof, he gets to watch the building collapse on the way down.
It's terrifying. Wow.
So the building, it was 74 meters long, 18 meters wide, and 5 stories tall. So not a small building, but also not a giant 40-story building. So the concrete slab in the building, so the slabs make up all the floors. These were constructed using flying forms or tables, which are they're pre-built plywood decks with metal frames, and they fly from one floor to the next as they build typical floors. All right, so the floor slabs, they were cast in 2 phases, and the roof, they did it all in one concrete pour.
So that kind of gives you an idea of how big the floor plate is. Still 74 by 18 meters is the floor plate, but it was large enough that they broke it up into 2 separate pours. So it was a decent size slab.
At the time of the collapse, the exterior walls were in place on the main floor and the second floor, and masonry or block walls were built on the main floor, second and third, and the material was placed on the fourth floor. So when you're building buildings, and Nicole can probably speak to this a little bit better than I can, there's a whole bunch of staging of materials, and there's different things happening on different levels as the building goes up. So as they're building higher floors, they can start on some of the masonry and the interior work and running electrical cabling and plumbing as they build the floors up, but they need somewhere to store the materials.
Yeah, so I think, at first I thought, they'll build the whole structure and then they'll come in and kind of do everything else throughout the whole building. But that's on a shorter building that might occur, but especially on these taller buildings, usually what happens is the structure goes up and then the exterior wall follows the structure, a few floors behind it to build the envelope of the building and get the building watertight. And then from there, they do the interior framing, then mechanical, electrical rough-in. Then they'll come behind with the drywall and the fixtures, finishes, tile, paint, etc. So the building does go in stages as they kind of move workers throughout. And we do talk a little bit about this later on in the episode, but as they're pouring the upper floors, they do leave temporary columns, which are called reshores, on lower floors just until the concrete has set. So they usually keep a certain number of reshores for a certain length of time. Usually, I believe it's usually about 28 days to fully cure the slab, depending on the mix and the requirements. And so they'll leave those, either all of or some of those reshore columns in place until the slab has cured for a certain number of days or until the structure is a certain height above that slab. And so, again, we'll talk about it a little bit later, but there was some issues with the reshore on this project as well. One of many, many issues. Again, if anything that could have gone wrong with the structure went wrong with the structure, this is pretty bad. So just speaking of the workers in the building, I just want to mention, looking at the report for this collapse that was done, which I'll get into shortly, there is a drawing on our website that indicates the approximate location of all the workers in the building at the time of the collapse. And that drawing does tell us which workers survived and which ones unfortunately didn't. And it's just interesting to see because, there's some workers that were in the middle of the building that survived and some workers that were on the roof that didn't. And so it's kind of interesting to see, maybe a little bit morbid, but it is interesting to see how different people were able to survive a collapse like this, where the entire building just basically pancaked on itself.
So what was the cause of the collapse, Nicole?
Well, the National Bureau of Standards performed an investigation at the request of OSHA, the Occupational Safety and Health Administration. The ultimate cause, the official cause, is known as low punching shear capacity. The concrete slab was only 200 millimeters thick when it should have been 280 millimeters as per the American Concrete Institute's building code minimum. From the investigation, they found a design omission of a check for punching shear capacity, which led to the thinner slab. So there is supposed to be an additional check that's done by the structural engineer for punching shear capacity. They didn't do this. It was omitted from the design for whatever reason, and that's what led to the slab being 80 millimeters thinner than it should have been.
Yeah, and it doesn't even really seem like they're close on this slab thickness. Missing it by 80 millimeters or 8 centimeters, I guess right around 3 inches for non-metric listeners. Like, that's a significant thickness of slab that they're short.
Oh, it's almost 30%. So the slab was about 67% of what it should have been, which is pretty bad.
Yeah, they missed it by quite a bit, and I don't know if later on in the construction process, if there would have been other issues just running anything through the slab or offsets for any other electrical or plumbing or piping, just with having a much thinner slab than I guess what it was designed to.
Yeah, one thing I will say, as tragic as this is, it's almost a good thing that the building collapsed during construction and not after everyone moved into it, that doesn't make it okay. That doesn't make the loss of life okay. But what I mean is that this could have been significantly worse than it was.
Commenting this problem was the plastic chairs as well that would support the rebar. So these were 110 millimeters tall. They were supposed to be taller than 110 millimeters. So this reduced the effective depth or the thickness of the concrete below the top layer of the rebar. Like I said, the chairs supporting the top layer of the rebar, they were too short. Cover was supposed to be less. So it would have had more concrete under the rebar.
So essentially the rebar, if you're looking at the slab in section, the rebar should have been closer to the top of the slab depth, but it was much lower in the slab. So you need a certain amount of slab coverage underneath that top layer of rebar, and they were about 25 millimeters or an inch short.
Yeah, so it was supposed to be 19 millimeters of coverage, and they wound up with 44 millimeters of coverage. So over double what they should have had. So the shop drawings from the steel supplier, they did outline the number and the sizes of these chairs, and these were just marked as approved as noted, and the engineer just signed off on them. So we're not really sure why they were missized.
So going back to the punching shear capacity, the columns were believed to have punched through the 5th floor slab in one location, and then this caused the entire 5th floor to collapse, and as we mentioned, pancake the slabs below it until the entire building was collapsed. They believe that the collapse initiated at column G2, which was an interior column, and it supported the latest bay of fresh concrete on the roof. Concrete had been placed on 7 of the 9 forms on the roof when the collapse had occurred. So they were 7/9 of their way through the roof pour at the time of the collapse. There was reshore on some of the lower slabs. So these are temporary columns that are put in place until the concrete's had enough time to cure. And these reshore or temporary columns, several were in place at the time of collapse, but they are a little bit fuzzy on where those were.
Nicole, with the reshore columns, just since I don't work in building construction the same way Nicole does, are those laid out on engineering drawings for where they should go, or is it kind of a, put in reshore, column somewhere kind of at the discretion of the contractor, the engineer on site? Like are those reshore columns laid out to be placed specifically anywhere?
Yeah, so there is a reshore plan. I'm not part of this discussion, so I don't actually know whether, I'm assuming it comes from the structural engineer, but it might come through the general contractor and then get reviewed by the structural engineer to make sure it's accurate. And oftentimes there'll be a full layout with a ton of columns, maybe every 5 feet, 4 feet, 3 feet, whatever it is. And then as the concrete cures, they can reduce some of those. So they don't necessarily need to keep all of those columns for the entirety of the cure. They may reduce the amount of reshore columns kind of as the concrete sits for more and more days.
Yeah, I didn't know they were called reshore columns. I've seen them. So downtown Calgary where I live, there's a ton of new building construction that's happened for residential towers and some newer commercial office space towers. So when I was walking to work or walking around downtown, I would always see these, they pour the concrete slab and then, they keep going up with the crane. And they had these temporary columns in there. And I assumed that it was to support the slab above it, but I had no idea that they were called reshore columns.
Yeah. So, they're obviously necessary, but I will say, especially when they're densely located, they do make moving around on the floor pretty difficult. And obviously you can't really build any of your interior framing until those are complete. It's hard to work and get, exterior windows or the exterior wall complete. And so it is ideal to get those removed, as soon as safely possible so that you can get working on your interior finishes. So according to the general contractor's reshore plan, the 2nd, 3rd, and 4th floors were supposed to have full reshore, so the maximum amount of those columns that they needed. But based on worker accounts and information that they uncovered during the investigation, they believed only the 4th floor had the full reshore and the main floor had only a few exterior reshores. The 2nd and 3rd floors were unclear. So the plan said all of them were supposed to be on 2nd and 3rd, but workers said there was none or very few, but they kind of got conflicting responses from people. So they weren't really sure, but they kind of assumed that they didn't have the full amount on those floors. Here's another big problem that I have a significant issue with. So the concrete for these slabs was provided by a ready mix plant nearby, and an on-site batch plant. So if you'll remember the CN Tower episode that we did in episode 40, Engineering Marvel, a little bit different. That one went a lot smoother. They also had an on-site batch plant. This one was not as good. So the ready mix plant provided about a third of the concrete for the slabs, and the on-site provided the rest for the slabs. And then the on-site batch plant also provided all the concrete for the columns. But that batch plant was reported to have non-uniform consistency and finishability.
That's not good when you're dealing with concrete.
Nope, not good at all. And the proportion of each ingredient did not seem to be consistent across all the samples that they tested. So it was basically to an extent, a free-for-all for each batch. It doesn't seem that there was any specific recipe that they used. So the ingredients might not be in the same proportions. Maybe the mix time was a little bit different. And so the results of these concrete pours was completely inconsistent. Not only did this affect the strength of the structure, but it also affected the finishability of the structure as well. So the developer had a superintendent on site, and he oversaw the batch plant operation. But he was away from February 2nd to March 9th. And the second and third floors were placed during this time and appeared to have the most erratic slump in their concrete. So the leveling of the concrete on the second and third floors was off by somewhere between 75 to 225 millimeters, which is a lot.
That seems like a lot.
That would not pass quality control standards at all. Is bad.
Like that's on the upper end. I mean, that's 20 over 22 centimeters, over 8 inches of difference.
Bad. And then on top of him being away, the general contractor superintendent was also away on the week of March 2nd, and the third floor was placed while he was gone. One of the concrete finishers noted that the texture and slump of the concrete became more consistent once both of those superintendents had returned. So not only was the mix inconsistent on a regular day, but then the two people running those batch plants, when they were away, it just got much, much worse. The masons or the block workers, they also found some of the concrete difficult to finish and that it set up really, really quickly. That said, this only appeared to be an issue with the batch plant on site, and they thought it was due to low water content and a lack of super plasticizer, which is added to concrete trucks prior to placement and ensures a more consistent finish of the concrete. Not surprising, core samples from the slabs and columns were removed from site for further testing. While those samples satisfied the American Concrete Institute code, the column samples were of lower strength than the slab, and the fifth floor column samples specifically didn't satisfy the American Concrete Institute requirements.
So yeah, that's at least 3 things, probably 4 things that have led to the collapse of this building.
And we're not done. So far we have the slab thickness, the concrete mix, and the rebar placement, or the chairs, the depth of the chairs that were holding up the rebar. And there's more. We're not quite done. On top of all of those things, many workers who were interviewed noted cracks in all of the slabs. The structural engineer walked the site on March 10th, 17 days before the collapse, and the second and third floors were in place at that time. They recommended that additional rebar be added in the midspan of the walkways. So they didn't really have a solution for the slabs that were already poured. And then when plumbing sleeves, so when you pour the concrete, you know where all of your vertical pipes are going to go. And so they put sleeves or cans in place during the pour so that they don't have to go and cut those out later. They've already basically made a hole in the slab to run their pipe up later. So when those sleeves were removed during construction, some of the, quote, spider cracks could be seen extending 102 to 127 millimeters into the slab. So when you removed those sleeves and you looked at the thickness of the slab through that hole, you could see the cracks extending. That's over halfway through the depth of the slab. So that's pretty significant. It's not on the surface. It's through the depth of the slab.
Yeah, that's not good. Any cracking in concrete, especially right after it being poured, is not ideal by any stretch of the imagination. So like Nicole said, we're still not done. So there were noticeable slab deflections that were witnessed as well, and these were most evident on the north and the south ends of the building. So they noted a 45 millimeter deflection on the north end of the building on the second floor. So with that, there was a water puddle that formed during placement of the roof on the east side of the building near the elevator shaft. Workers used extra concrete to fill the depression, but it reappeared after finishing again. And then a similar problem also occurred at the same location when they placed the fourth floor. So they have a lot of issues with the building not being level and this poor quality of concrete pour, and trying to solve problems, I think, with poor quality concrete. So there's all these problems that just seem to compound and ultimately lead to the roof collapsing with the rest of the building. Additionally, the workers mentioned that the construction joints were not of good quality, and they described these as ragged, cracked, and honeycombed. So there was rebar showing on the faces of some of the columns. Incomplete filling of the column form was likely due to steel congestion, and it was noted in some cases the steel congestion was so severe that the slab steel could not pass through it on the second and third floors. So that's really bad. So this ultimately prevented the development of an adequate bond between reinforcing bars.
So to recap, we have the slab was too thin by a third. The chairs were too short, and the amount of concrete below the top level of rebar was too thin by about 25 millimeters. The concrete mix was inconsistent, which led to slumping of significant amounts across the slab. There was deflection, there was cracking, there was rebar that was too thick, which was preventing concrete from getting into some of the columns. Did I miss anything? I mean, that's a long list of issues.
I'm actually wondering why they didn't stop construction on this project before this collapse. Like, this is not one or two minor issues that they're experiencing on this building. Like, I feel any one of these issues is a fairly major issue in a construction project.
So I think, cracking does happen, and to an extent it's okay as long as it's surface cracking. I don't know what that threshold is, but I have seen cracks, and I have seen them reviewed and by multiple parties and then deemed to be, surface cracks and acceptable. I think, the slab thickness, the chair depth, the concrete mix inconsistencies, while we look back and see those now, I don't think they were aware of those issues at the time. I think, it sounds like the structural engineer was on site on a somewhat regular basis, and they were there, a few weeks before this collapse, and they gave the okay. They said everything was fine. And so I think that the developers and the contractors were trusting that they were correct, and that they, yes, there were issues, but they were manageable issues and they were okay. Nowadays things are a little bit different. Nowadays they would take a sample of the slab or the concrete mix as they're pouring, and then they would test that sample. Usually I think they take a few samples and they test the strength of that sample at certain days of cure time. And so usually the results of that sample, I think, help them assess the reshore plan and figure out when and how they can remove those columns. I don't think that happened here. Also nowadays, on-site batch plants just don't occur. We don't really do that. It's not really feasible. Getting concrete from a plant, in the city you're developing, you get a lot better results, a lot more consistency. There's no issues with delivery. It's just the process goes a lot smoother.
Yeah, I did work on a project quite a number of years ago in northern BC, where we did have a batch plant on site because we were more than 3 hours, I believe, from any center that could deliver concrete in a timely manner. And it was also, we were building this project in winter. I was there for quite a few months in the winter, and it was consistently below minus 25 degrees. So having the batch plant on site certainly helped out quite a bit with the concrete pours. Otherwise, the trucks would have had to come, I believe it was 4.5 hours for them to get to the site that we were working on. So that was fairly remote, and obviously if it was that remote, they wouldn't be building a 5-story tower like this. So yeah, like Nicole said, for in-city construction now, I feel batch plants aren't as common as what they were before.
Yeah, I mean, I've done most of my work in large cities. I've never seen on-site concrete mixing. I don't think ever. I mean, I'm not structural, so it's not something I'm specifically paying attention to, but it's also not something I've ever seen. So, this failure was 40 years ago. And so I think this was before a lot of the safety mechanisms that we have today were in place. I think a lot of lessons were learned out of this failure. Of course, still tragic, but, this is a big reason we're doing this podcast, because looking back on this failure, there's a lot to learn here and a lot of things, a lot of don't do this. And so I think looking back at these types of things and these types of accidents is really, really important so that we can learn from them and stop them from happening again. I've said this before, failure is an integral part of engineering, and we need to look back at failures to figure out what went wrong, why, and what we can do to prevent it from happening. So, as tragic as this is, I do think this is really, really important. As are all of the failures that we've covered. Really, really interesting, really, really important. So after the collapse, 2 engineers, an architect, and 2 contractors were charged with negligence and failing to follow state and local codes. Both engineers surrendered their license to practice in Florida. The primary engineer, who was 59 at the time, paid a $3,000 fine.
That doesn't seem like a lot at all.
It's not.
Even in 1980 dollars.
Yeah, so it's about $9,000 today. So yeah, that's not very much. The other engineer also paid fines, and they both agreed to never practice in Florida again. The general contractor folded almost immediately, and interestingly enough, the developer settled out of court, and they continue to develop properties today, which is interesting. I don't know their name. I'm assuming they've changed their name if not twice. I'm not sure who they are, but according to the articles I've read, they continue to practice today. So hopefully they learn from this.
Well, I hope they haven't had any subsequent buildings collapse.
No, I think they learned their lesson.
I hope so. So there you have it. The Harbor Cay Condo construction collapse in Cocoa Beach, Florida. 2 main issues with thickness of the slab and the height of the chair supporting the upper rebar, as well as a ton of minor issues, led to a structure so weak it couldn't even support itself and collapsed before the roof was complete. And like all of the failures we've covered to date, this one was also completely preventable. Like Nicole mentioned, there's a lot of lessons to learn from this failure, and I hope that the structural engineers around the world were paying attention to prevent something like this from happening again.
For photos, sources, and an episode summary from this week's episode, head to failureology.ca. If you're enjoying what you're hearing, please rate, review, and subscribe to Failureology so more people can find us. If you want to chat with us, our Twitter handle is @Failureology. You can email us at thefailureologypodcast@gmail.com. You can connect with us on LinkedIn, or you can message us on our Patreon page. Check out the show notes for links to all of these. Thanks everyone for listening, and tune into the next episode where we'll tell you about the Challenger space shuttle. 72 seconds after takeoff, the Challenger exploded in air on live TV in front of millions of people. But more on that next time. Bye everyone. Talk soon.